If you remember back in the fall, so many months ago, we did some gram-mole particle conversions, and we had this chart here where you could convert the mass of an object using its average atomic mass off the periodic table, the formula mass, to convert to how many moles you have. And you could convert between numbers of things, atoms and molecules, and the mole, using Avogadro's number of 6.02 times 10 to the 23 particles per mole. So this is a way for you to figure out how many atoms you had of a particular substance based on its mass and its formula mass off the periodic table. We also talked briefly a little bit about gases and how you could convert a gas into moles and into grams or into numbers of things. And the good thing about gas is that it didn't matter what the gas would. Could be oxygen, carbon dioxide, could be vaporized iron. And it would, 1 mole of that gas would occupy 22.4 liters. 1 mole of any gas at standard temperature and pressure occupies 22.4 liters. So we had our conversions here, and they were all what 1 mole equals. 1 mole is that many particles, 1 mole is the molar formula mass, or 1 mole is 22.4 liters for a gas. And we've been doing BCA tables of solids, basically, so we've been converting from masses of substances into moles and then doing BCA calculations. Well, now we're in a little bit, we're going to start to concentrate on doing BCA calculations for gases, but the conversion's real easy. You can convert from volume of gas, because you can't put it on a scale, just the volume into moles, do the BCA calculations just like we did with solids, and figure out how much of something we have. All right, and as an example today, all I wanted you to do was convert the mass of that big helium balloon they use down there at Conner Prairie that probably most of you have at least seen, if not ridden in. Well, it's a 17 million liter balloon. Okay, so we have the volume of the gas, and I'm asking you for what is the mass of the helium in it. I know it's 17 million liters, but I want to know what the mass is. We can't go straight there. We can't do one conversion to get to molar mass, but we can convert that 17 million liters into moles, how many moles of helium there are in the balloon, and then we can use the molar mass from the periodic table of helium and convert that to grams. So you had the 17 million liters. We went ahead and multiplied by the conversion that 1 mole of any gas is 22.4 liters. I put liters in the denominator because they were in the numerator and I wanted them to cancel. You do this, so 17 million divided by 22.4 is 758,000 moles of helium. So I've gone from volume of the gas to moles, and now I can use the periodic table number for helium and convert to what it weighs and what its mass is. And so 758,929 moles of helium, and the conversion is that 1 mole of helium is 4.00 grams. I put the moles in the denominator and the 4 grams in the numerator because I wanted to change from moles to grams. They cancel, and I'm left with 3,035,714 grams of helium, or a little bit more digestible number as you divide by 1,000 to convert it to kilograms. So it's 3,036 kilograms, so a little over 3 tons of helium in that balloon. And you wonder, why, how can a 3-ton balloon float? Well, because it displaces 17 million liters of atmosphere, which is a little more than 7 times as heavy or as massive as the helium. So it's 3,000 kilograms of helium in this balloon, but it would be somewhere in the neighborhood of 22,000 kilograms of atmosphere. So the balloon floats, it's less dense. Okay, and we still talking about gases here. And remember, an important concept for us is these relationships between the pressure of a gas, the volume of a gas, the temperature, and the amount of gas. So P, V, N, and T. And the important thing to remember is that these are all kind of sensible. Like if you take this one in the middle here, N is the amount. This is a direct relationship between amount and moles and pressure. You know that if you have a balloon and you pump a little more air into it, the pressure is going to go up. If you pump more air into your tire, the pressure is going to go up. It's a direct relationship, a positive slope. Okay, so as amount goes up, pressure goes up. It's also true for amount and volume. If you hold pressure and temperature constant, if you add more gas to the container, the pressure or the volume will go up. It'll get bigger. It's also true for the relationships between temperature and pressure and temperature and volume. As you increase the temperature, if you hold the amount of gas and the volume constant, the particles start to move faster. They press against the container, and that's pressure. Those particles hitting the container wall, that is the pressure. So as the temperature goes up, the pressure goes up. Temperature goes down, pressure goes down. It's a direct relationship with a positive slope. For temperature and volume, if you hold number of particles and pressure constant, as you heat something up, the particles move faster, and they'd push against the balloon, and the balloon would get bigger. The volume would go up. So temperature and volume have a direct relationship. One goes up, the other goes up. The only one, if you can remember any one of these, it's the relationship between the volume of a gas and a pressure. If you hold the amount of gas and the temperature constant, then I guess the easiest way to think of it is as if you increase the pressure on an air mass, like a balloon. So if you squeeze down on a balloon, you increase the pressure, the volume goes down. If you lower the pressure, the volume goes up. So this is where I had the balloon and the bell jar, and I removed the atmosphere, and the balloon got bigger. So the pressure went down, the volume went up. This is an indirect relationship. One goes up, the other goes down. Okay, these are important concepts to keep in mind when we're dealing with gases. And another concept is standard temperature and pressure. This is just something that we sort of set as a nice, easy way for us to do calculations or to think of gases, the temperature and pressure. Basically, at sea level, anywhere on Earth, on a nice, pleasant day, or indoors, okay? Standard temperature is the freezing point of water. So it's 32 degrees Fahrenheit, which is 0 degrees Celsius, which is 273 degrees Kelvin. These are all the same temperature, and it's what we call standard temperature. And for us dealing with gases, the important one is Kelvin. And I mean, by important, I mean it's the only one we use when we do gas calculations. And I'll explain in a few minutes why Kelvin is the only real scale that makes sense for doing calculations with. All right. But we do have a couple of equations that we can convert from Celsius to Kelvin, or Fahrenheit to Celsius and then to Kelvin. That Kelvin is just whatever degrees Celsius plus 273, and I'll explain where we get that 273. So if you're at 0 degrees Celsius, you add 273, and that tells you the Kelvin temperature, 273. If you have Fahrenheit, you can convert Fahrenheit into Celsius, and then use this equation to convert it to Kelvin. Degrees Celsius is equal to Fahrenheit minus 32, that quantity, divided by 1.8. That'll tell you the Celsius temperature. Then you can add 273 to get to Kelvin. Let me explain where that comes from. So the basic concept is, remember that the temperature of a particle is a measure of how fast the particles are moving. And how fast they're moving makes the volume of the gas. They're moving around and they're pushing out on the sides of a balloon or whatever, and they're making a certain volume. So if you have a temperature of a gas in a balloon at, say, 0 degrees, standard temperature, it's going to have some volume. If you heat up those particles, the balloon's going to get bigger because the particles are moving faster. They're going to push against the sides of the balloon and make the balloon bigger. If you heat it up even more to, say, like 100 degrees Celsius, the balloon's going to get even bigger. Heat it up more, the balloon's just going to keep getting bigger. Well, you can make these measurements, you can graph this, and what you can do is then extrapolate that data. You can make a really small, a lower temperature below 0, and you can get a smaller balloon. But that means you need to extend your temperature scale here into the negative values. And that's what's kind of bad about using Celsius and Fahrenheit, is that you have negative values. You can have a positive 50 or a negative 50. So when you're plugging these values into an equation, there's no difference between a balloon, a magnitude of negative 50 or positive 50, but that negative number is going to completely change the value of anything when you plug it into a calculator. You can also have 0, and you don't want to put zeros into equations because it makes a lot of stuff blow up. Okay, and we can extrapolate, draw a nice straight line as the temperature of the air goes up, in the balloon or whatever, the balloon's going to get bigger. Well, you can extrapolate that and just send that line on through, and you can say, well, even though I didn't test it, I can say, well, I've got a balloon way out here at this temperature, maybe 275, the balloon should be this big. That should be the volume right there. I can also extrapolate it in the other direction and say, well, you know what? I can, at negative 100, the balloon should be this big. It should have this volume. Okay. And that just means that you need to extend your scale even further out to the left. All right, and now you can start to see that volume there on the y-axis. You're going to get to the point where that volume reaches 0. That's right here. So it's really hot, makes big balloons. As you slow them down, they get smaller and smaller and smaller. But you're going to get it to a point where the balloon has 0 volume. And that point is what's called, on the Kelvin scale, absolute 0. That means there's no motion whatsoever in those particles in that balloon. They're not moving, so they're not pushing on the balloon, so the volume of the balloon is going to be 0. Or, the size of the atoms inside, because they're not pushing anymore. And at that point, all motion of that gas or those particles stops. The volume is 0. That is negative 273 degrees Celsius. So that line just extrapolates and crosses the 0, the x-axis there, right at negative 273. And that is, on the Kelvin scale, that's 0. So for Fahrenheit or Celsius, they're kind of silly scales. They're not real or absolute or scientific scales. Temperature is a measure of how fast a particle is moving. So how can you have negative values, right? And if you get to 0 on the Celsius scale, well, that should mean that the particles aren't moving at all, but it doesn't. The particles just keep slowing down. They just go into a negative speed. But the Kelvin scale, when you get to 0 on the Kelvin scale, that means no motion. This is an absolute scale. It's a true scale. And here, if you'll note, there's a few points here. 0 on the Celsius scale is 273 on the Kelvin scale. It's the freezing point of water. Water freezes at 273 degrees. On the Fahrenheit scale, which is even a little more silly, Fahrenheit is based on the freezing and boiling points of a mixture of ammonia and ice. So not really anything that anybody would have any real dealings with. But on the Fahrenheit scale, all motion ceases at negative 459, and water freezes at negative 32, and it boils at 212. So this Fahrenheit scale is kind of silly, and it has negative numbers and it has zeros, and that's not good for calculation. And Celsius has a 0 and negative numbers. That's not good for calculating. So when we do gas calculations, they have to be done in the Kelvin scale, because it's the only real scale that doesn't introduce a 0 unless the 0 is truly no motion or negative numbers. Okay? So standard temperature for us is 273 Kelvin. When we do gas calculations, if you don't have Kelvin, you must convert. Okay? And then standard pressure is, I'm sorry for Americans, but there are many, many units that we use. A standard one for like car tire pressure or something is 14.7 pounds per square inch. So every square inch of you or any object is taking 14.7 pounds pushing down on it from the atmosphere, because you're at the bottom of a pool of air, a 60-mile deep pool of air. That's the same pressure as 29.9 inches of mercury. It's the same as 760 millimeters of mercury. It's the same as 1 atmosphere, which is equal to 101.3 kilopascals, which is equal to 760 torr. So there's several different systems. You can use any of them, The international system down here is kilopascals, so the metric system is kilopascals. But we just like to use a bunch of, but that means you're going to have to do some conversions.